Welcome to Nonlinear Optics. What will we do today? Well, last time we were looking at the susceptibility tensor, certain properties, also I guess we did the anharmonic oscillator model and things like that. Even before we did phase matching, and before that all these second order nonlinear effects. Now, today we want to switch to third order nonlinear effects. And you may remember from chapter 2, I just show it here on the lecture notes, hopefully. So if I go back, all the way back, you don't see that, but no. Yeah. So we discussed in this chapter 2, where I gave a survey of nonlinear effects, we also discussed third order effects. So the idea there was a very simple one. We just wrote down the polarization as a function of different orders of power expansion series of the electric field, right? And then for the third order, we found, of course, this term here. We calculated, well, I'm not sure whether I really did it, but in principle, we can calculate here the third power of this. Well, in general, we would write it as a complex field, and but here we did it actually as a real field. And you see this here, yeah? So whenever I write E as a script E, I mean explicitly a real quantity here, in this case a real amplitude. And what we saw was that the polarization oscillates like the third harmonic of the initial frequency. This is what one would expect for a third order effect. But what we also saw, maybe to our surprise, and it is just a property of trigonometric functions, I have to emphasize. Yeah? So what we found because of these trigonometric functions and their properties, that there is a polarization that oscillates at the fundamental. And now if you go back even one chapter earlier, namely chapter 1, where I discussed the Lorentz model, there we said that the refractive index comes from a polarization that oscillates, well, in linear optics, of course, always at the driving frequency. Now, we have a nonlinear effect, but, yeah, so you see the nonlinear effect by the nonlinearity here of this amplitude, but we still have an additional contribution to the polarization oscillating at the fundamental. And therefore, it is, well, it is obvious to assume that something should happen to the refractive index. And, well, this is the topic of the lecture today. And actually, it is pretty much the topic of everything that follows through the end of this course. I will come to this perspective at the end of today's lecture. Well, let me go back to the current point where we are. Yeah, so we are at chapter 8, intensity-dependent refractive index, where we just take a few notes and write down what I just explained. So the first point is we have seen that for nonlinear processes, for nonlinear third-order processes, well, third-order processes should always be nonlinear, but never mind. For third-order processes, there is a contribution to the polarization P oscillating at the fundamental, at omega. at the fundamental. So we still have this problem. So at the fundamental. Yeah. So and our forecast is, so to say, yeah. So the forecast would be there should be a nonlinear contribution to the refractive index. To the refractive index. You might be tempted to say that, well, the refractive index is something, more or less boring in optics, but this is not so in nonlinear optics. Yeah, so the refractive index, when it starts to depend on the intensity, gives rise to very interesting effects. Okay, well, it's a third order process. So in principle, we can mix three colors. So in principle, we can distinguish between the degenerate case and the non-degenerate case. We will largely concentrate on the degenerate case. So this is annoying. We had it for repair, but apparently. Okay, well, let's write that down. Yeah, so we can distinguish between the degenerate case where all the frequencies are the same, and we'll concentrate on that, and but it's also possible to consider the non-degenerate case, and I will make a quick remark on the latter. So we can distinguish the degenerate case so all frequencies are the same. We just use a laser and shine on the material under consideration. And the non-degenerate case. And what we would typically have there would be, say, one field that is very strong, and then we would have kind of a probe field to which then something happens. Yeah? So degenerate case, so the frequencies are different. In general, there could be 3 different frequencies. The most important case would be a strong and a weak. Yeah, so a strong, and this we would call the pump, typically. A strong and a weak beam. And this would be the probe. Yeah. Well, but in either case, the polarization would be given by what we already had in the second chapter. The polarization. So if we write it in time domain, then we would have the third order polarization, and it is given as usual by the dielectric constant times here the third order susceptibility, and then the E field to the third power. Yeah? So that's equation 1. And we expect an intensity-dependent refractive index, and now think about what an intensity-dependent refractive, or what the refractive index is doing. Well, it is changing the phase of the field as compared to, say, a plane wave that co-propagates outside this material, right? Okay, so we write that down. So how should I word it? So the intensity-dependent refractive index should, well, now I can use different words here. I could say it should alter the phase as compared, say, to a weaker field. But I also could say it would modulate the phase. Now, so particularly clear is this in the, say, in the non-degenerate case. There you have, say, the probe beam without the pump beam, and then you apply the pump beam, and suddenly the phase of the probe beam is changed, is modulated. Yeah, so the intensity-dependent refractive index should modulate the phase of E of t. Yeah. And now, if we look at the degenerate case, then the beam modulates the phase of itself, yeah? And we call this self-phase modulation. Okay, let's go to this case, to this degenerate case, and we'll largely concentrate on the degenerate case. Well, you will learn why this degenerate case is so interesting. So this is the next chapter, 8.1. 8.1, the degenerate case. And our first goal will be to derive an expression for the refractive index. But in order to do that, we pretty much have to start there where we also started in chapter 2. So, well, for the degenerate case, there is just one input field. Yeah, so there is just one field, and we write it in complex notation in contrast to what we did in chapter 2. So we write E of t is equal to the amplitude times e to the minus I omega t plus the complex conjugate. So, and now we need to do the cube of that. Yeah? So according to equation 1, we need to compute, well, the cube of that, of course, right? And because this is a lot of work to write, I just copied the respective, well, quick calculation from the script. So, and here you see it, hopefully, if it would work. Yeah, so here we have it. Yeah, I just stupidly multiplied out this product here. And what you see is that we get different terms. So here we have the third harmonic, right? This one here is the complex conjugate of this one here. And then we indeed have the fundamental. Again, so you see this here is the same. So we have 3 times e squared e star, e to the minus I omega t. And then we have the complex conjugate of that, right? So 3 times this thing here. So if we write that down, so the result, then we see that we get e cube e to the minus 3I omega t plus the complex conjugate. Well, I guess I should start a new page here. So we have e cube e to the minus 3I omega t plus the complex conjugate plus 3 times e star e to the minus I omega t plus the complex conjugate. Equation 3. Right? So therefore we can write a term or an expression for the polarization that oscillates, for the third order polarization that oscillates at the fundamental. So the third order polarization oscillating at omega is P3 of omega, and this is 3 times epsilon 0 times chi 3 times E of omega, and the complex conjugate of omega. And you know that this product is the modulus squared of E, and then times E of omega. So this thing is the modulus squared. Equation 4. Yeah? So now if you compare this, this expression with what we did in chapter 2, then you might remember, if you had a quick look at what I showed in the beginning, you might remember that instead of just a factor of 3, there we had a factor of 3 divided by 4. And now you could ask, what is right? Well, yeah, so what is the reason for the difference? The reason for the difference is that in chapter 2, we avoided any ambiguities by calculating with real numbers. And here we use complex notation together with this questionable convention in nonlinear optics that we write e to the I omega t not as 1/2 of cosine times I sinus, but we drop the factor 1/2, right? And this gives rise to all these, apparent problems. Anyway, this is how it is done in nonlinear optics. Okay, well, yeah, let's perhaps write down this remark. So a remark in chapter 2, we had 3/4 instead of 3. Because here we use the questionable convention e to the I omega t is equal, well, I put it in quotation marks, to cosine omega t plus I sinus omega t. Yeah, so we drop the factor 1/2. That should be there in principle. Okay, so far, so good. Everything trivial pretty much, right? The next step that we want to do is to derive an expression for the nonlinear refractive index, and you'll see that this is also pretty much a trivial procedure. So let me write that down. Derivation is actually a little bit, I said a little bit too much. Derivation of the nonlinear refractive index. So, well, it is clear that, well, we have this third order nonlinear polarization that oscillates at the fundamental, but we also have the linear part. And what we do next is just to write down the entire polarization, the total polarization that oscillates at the fundamental. And then we can relate this to the refractive index. So the total polarization oscillating at omega is, well, the sum of the linear part and the nonlinear part. So P total of omega is equal to P1, the linear part of omega, plus P3, the nonlinear part. And if we write down the respective equation, then we would have here epsilon 0 times chi 1 times the electric field plus 3 times epsilon 0 times chi 3 times the modulus squared of the field times the field itself, right? And, well, it is obvious that we can factor out the electric field, and then this expression here looks pretty much like the expression that we would write down for the linear polarization alone, right? So what we can write here is, of course, epsilon 0 times, how do I write it? Yeah, chi 1 plus 3 times chi 3 times the modulus squared of the electric field. And then I put these brackets in fat. So like this. Yeah? And what we do is that we compare it to the expression that we would have for the linear case, and then we would identify this expression in brackets with kind of an effective susceptibility, right? Okay, let's do that. 6, compare to P1 of omega is equal to epsilon 0 times chi 1 times E of omega, so which is the linear case. So this motivates Yeah, because in the linear case, we would go on and then relate this expression here to the refractive index, and we are going to do the same thing here. So this motivates to write chi effective is equal to the linear susceptibility plus 3 times the third order susceptibility times the modulus squared of the field. So that's equation 8. And in the same way, we would, of course, write then the total polarization, yeah, such that it looks like the equation that we have for the linear case. So the total polarization then would be written as epsilon 0 times the effective nonlinearity, the effective susceptibility, times the electric field. Right? So and the point is equation 9 has exactly the same form as P1 of omega equals, well, what I just wrote above here. So, and this is used to find an expression for the refractive index. So this we use to find an expression for the refractive index, for the nonlinear refractive index, of course. And to this end, we remind ourselves how we did it for the linear case. There we have that n squared is equal to 1 plus the susceptibility. Yeah, so in the linear case, we do this by using n naught squared is equal to 1 plus chi 1, right? So then here we would have that the square of the intensity-dependent refractive index should read 1 plus now the effective susceptibility. And if we use equation 8, then this is 1 plus chi 1, which is still, of course, the field-free refractive index. So, what was this here? So n naught squared plus 3 times the nonlinear refractive index, so third order susceptibility, not refractive index, times, of course, the modulus squared of the electric field, right? And maybe it is a good idea to remind ourselves what this thing is. So here on the left-hand side, I already wrote intensity. Here I still have the electric field. So we should say what the relation of electric field and intensity is. Yeah? And this is 2 times n naught times the field constant times c times so this here squared. Yeah? So this is the intensity. And therefore, and therefore we find that n squared of I is equal to n naught squared plus 3 times third order susceptibility times the intensity divided by 2 n naught epsilon 0 times C. Yeah, and that's probably equation 10. Yes. So we wanted to have an expression for n, but we only have one for n squared. What do? Of course, we do a power series expansion, a pretty simple one here. Yeah, so a linear expansion of n, of n of I, n as a function of the intensity. Well, and this means, of course, that we would approximate it by n naught plus n2. So we call the nonlinear refractive index, we would call it n2. So we already know that it depends on the intensity in a linear way according to this here, right? And of course, this n2 will be a very small number as compared to this one here. Actually, the entire thing should be, so n2 times the intensity should be small. Otherwise, this power series expansion would break down. So this expansion is obviously justified, right? And this equation, which we call equation 11, this we just plug into the left-hand side of the equation of equation 10. Yeah, so 11 in 10. Then we get n naught squared plus n2, n naught plus n2 times the intensity and this here squared. So there we would get a term that is proportionate to I squared, but we drop that. So we just have n naught squared plus 2 times n naught times n2 times I. And now this should be equal, according to equation 10, this should be equal to n naught squared plus 3 times chi 3 times the intensity divided by 2 n naught epsilon 0 times C. And now you can just compare the terms. So you would see, for example, that this here goes to 0, and then we can solve here for n2. Then we find that n2 is equal to 3 over 4 times 1 divided by n naught squared epsilon 0 times C times chi 3. Right? And this is, of course, a fairly important equation. So we frame it like this. Yeah? So equation 12. What we can do is to find, to calculate this prefactor, so such that we have kind of a handy equation. So if we put in numbers, quantities, then we would find that N2 in units of meter squared over watts. Yeah, so this is obviously the unit of N2, because if we multiply it with the intensity, which has units of watts per square meter, then we should get a quantity with unit 1. So this must be the unit here. And then we would have 283 divided by n naught squared chi 3 times meter squared over volt squared. Yeah? So this is the unit of the susceptibility. So that's equation 13. Yeah, so now we could ask ourselves, if we speak about third order effects, how large is this chi 3? We made an estimate in chapter 2, I think, but here it might be interesting to really look at it. And I have a table for that, because the answer is, it depends. So let us see. So here's this table. So it depends actually on the mechanism that is responsible for the nonlinear polarization. If we speak about electric polarization, which we do most of the time here, well, pretty much all of the time, so more than 90%, I would say, then you see that the magnitude of this second or the intensity-dependent refractive index is, well, here in units of centimeter squared over watt. Not meter squared over watt, but centimeter squared over watt. It is 10 to the minus 16. It would be 10 to the minus 20 actually in terms of meter squared over watt. No, the other way around. And, well, electric polarization means that we wiggle this electron. Yeah, so this is the reason. So think about the Lorentz model. And because the electron is so light, the response time is very fast. So it's on the scale of femtoseconds or sub-femtoseconds, right? And it has only been recently, just a few years ago, that one got direct access to this time scale via extreme nonlinear optics. Well, if we speak about molecular orientation, so you know that the polarization of molecules is different depending on their orientation. It makes a difference if, say, your nitrogen molecule is aligned like this to the electric field, assuming that it oscillates in this direction, or like this, still the electric field oscillating in this direction. Right? Then you can, so it's pretty obvious that if you think about a spring model, right, that the electron, that it might be easier to displace the electron in one direction as compared to the other direction, and therefore the polarization would be different, and therefore the nonlinear index of refraction would be different. But of course, the molecule is much heavier than the electron, and therefore it takes much longer to align the molecules. Now, if they are not aligned, then of course it makes no difference in which direction the electric field oscillates. And therefore, the response time is 3 orders of magnitude lower. Well, and then there are other possible effects. Yeah? So thermal effects is an interesting one, a very important one. And this goes, of course, on the scale of milliseconds or so. Yeah? And actually, thermal effects is kind of different from many other effects that we usually discuss. Namely, if you have thermal effects, then heat conduction can cause different temperatures at points where you do not change the intensity. Right? So changing the intensity at one point can change the refractive index at another point. And so in this sense, this kind of effect is non-local in contrast to the case for electric polarization or molecular orientation. Okay, so we have an expression for the nonlinear refractive index in the degenerate case. And now we could do the same thing for the non-degenerate case. I did it in the script. Here I just want to give the result. So let's put the headline. That would be 8.2, the non-degenerate case. And I will make it short. So it is straightforward. I just will write. So it is straightforward to derive that in this case, so this kind of cross talk between two electric fields, that this is twice as large. And we have 1 over n naught squared divided by epsilon 0 times c times the third order susceptibility. And if you want to see the details, I would like to refer you to the script, because we want to go on and not spend too much time on some consequences. Well, there are two kinds of consequences that we can now discuss. And you'll see that the important ones, at least to my modest opinion, that the important ones are those that depend on time. But of course, the other ones are, so it would be totally inappropriate to say that they aren't important, but they are also spatial effects. Yeah? And these we want to discuss first within this lecture, and we will go on with temporal consequences or with consequences in time domain in the next lecture. Okay, 8.3, consequences in spatial domain, and the consequence that we discuss is actually self-focusing. So self-focusing. So the point is that when you take a beam of light, then you will always find that the intensity across the cross-section of the beam is not the same. So the most familiar laser beam is, of course, a Gaussian beam, where the intensity varies according to a Gauss-Bell function across the beam, which means that in the very center of the beam, on the beam axis, the intensity is highest, and as you go outside to the wings of the beam, you find that the intensity drops like an exponential squared. Now, if you think about what we just derived, namely the nonlinear refractive index, then you would find that the refractive index on the beam axis is higher than at the wings of the beam, right? And maybe some of you already guess how one would continue in order to analyze the situation. But let's first write down a few notes. So for all laser beams, the intensity varies across the beam profile, the cross-section of the beam. Yeah. And this means the refractive index. Varies across the beam. So the special case would be a Gaussian beam. So a Gaussian beam. And there we would have the highest refractive index on the beam axis and just the field-free refractive index and not at the wings of the beam. Okay, so the prediction is that we have self-focusing. This is what the headline suggests. And how can we derive that, or how can we substantiate that? Well, here's a small sketch. So think about it as a Gaussian beam. So we have a Gaussian beam. So the strongest or the highest intensity is here on the axis. And it falls on, say, just a block of glass. And then you would see that here the refractive index is higher. The refractive index is higher for the central beam as compared to a marginal ray. And now think about Fermat's principle. So compare this here to the case of a lens. Right? So in a lens, we have a longer optical path here than outside here. Right? And the consequence is that all passes that have the same optical lengths that they meet in the focal point. And we have exactly the same thing here. We have a longer optical path length here. Then we would have if the beam would go straight on. Right? But because, so as a consequence, it will deflect, and therefore also its optical path length will get larger because the geometrical path length increases. Okay. So we could note even for a rectangular block of glass. Ja, ich habe es gesehen. Even for a rectangular block of glass, we have a similar situation as compared to a lens, or some of you may know a so-called gradient index lens. So these are lenses where the glass is manipulated such that that at some position in the glass the refractive index is higher, and then you can use even just a parallel plate of glass in order to focus. Yeah? So even for a rectangular block of glass, we have a similar situation as compared to a lens. And we use Fermat's principle in order to analyze that. So the third point would be find what I call here the self-focusing angle. So this angle actually, right? Find the self-focusing angle theta SF by Fermat's principle. So one remark here. Don't get confused about this angle. So if you think about it, then it's of course clear that the intensity will increase as you go through the material, right? So the intensity will increase, and therefore this effect of self-focusing will steepen as we propagate through the beam, through the glass. So this angle here has little relevance, but we are actually more interested in this angle, right? So this here doesn't depict the physical situation, so this one here, as in contrast to this one here. But of course you see that we have here the same angles. It's just a geometrical construction in order to find this angle here, right? So Fermat's principle. Fermat's principle says that the optical path length, which I call OPL, which is defined as the integral of n times, distance, of course, that this should be constant. And we do this here by comparing the marginal ray and the central ray. So for the marginal ray, we have that n is equal to n0, yeah, so the intensity is negligible, and therefore the optical path length for the marginal ray is given by n naught times what I call here the self-focusing distance. Yeah, so this is, so it's actually written here. Yeah, so the self-focusing distance divided by the cosine of this self-focusing distance. Yeah, so good. So this is equation 32. And then we do the same thing for the central ray. There, of course, n is intensity dependent, so n naught plus n2 times the intensity, and therefore the optical path length of the central ray is n naught plus n2 times the intensity times this self-focusing distance. Yeah? And as I said, this is valid only at the entrance phase. So, okay, remark 32 is valid only at the entrance phase. Yeah, but this doesn't matter, right? But we are mainly interested at SF at the entrance phase. Yeah, so for us it is good enough. Good. Next step would be that we try to get rid of this cosine in equation 32 by a power series expansion. We say that the effect is small, because N2 is small. Well, we can, of course, increase the intensity nowadays, well, almost without limit. So we certainly can break down this approximation, but nevertheless, we'll start with this approximation. So a Taylor series expansion namely that the cosine of the self-focusing angle is approximated by 1 minus, and now the square of the of this angle, and this we would plug in into, we would use Fermat's principle and plug this equation 34 into our equation. Yeah, so the optical path lengths of the marginal ray should be equal to the optical path lengths of the central ray. And this means that N naught plus N2 times the intensity is supposed to be equal to N naught divided by 1 minus 1/2, so this is equation 34, and the square of the self-focusing angle. Right? And this can be, well, you have to multiply with the numerator here, and then you can simplify it a little bit. And after a few simple steps, you find that the square of the self-focusing angle is equal to 2 times N2 times the intensity divided by N naught plus N2 times the intensity, and this is approximately, once again, we neglect this here at this point, because, well, here it is important, of course. So this you wouldn't neglect, of course. So you wouldn't, you can't neglect it here, but here you can neglect it because this just makes a small correction to N naught. So, therefore, we can write 2 times N2 times the intensity divided by N naught. And then, of course, you can also take the square root and really get the angle. So we have 2 times N2 times the intensity divided by N naught. That's equation 35. Okay, yeah. So we found something. Well, And this was discovered at some point, and let me show the picture of that. So this is so this is a photo which is now, well, 60 years or so. Yeah, so it was made in almost 60 years. It was made in 1964. At that time, by Michael Hercher. So one of these persons is Michael Hercher, working at Rochester, and he discusses with a colleague. Unfortunately, the description of the picture doesn't say which of both he is. And at that time, they had ruby lasers that were intense enough in order to self-focus so steeply that optical damage would be induced. So this was a very surprising discovery at that time. So Michael Hercher was a graduate student at that time. So he just took his laser and let it impinge on a piece of glass or so, and observed optical damage. Also, the intensity of the laser was by far lower than the damage threshold. So what had happened was self-focusing, and one could see the structures, well, say under the microscope if you illuminate it from the side. Right? So probably the laser came, I'm not sure from which direction, from up, above or below. I would guess from above, but I'm not sure. Okay, so this was a very important discovery and provoked a lot of interest at that time. Not because of the damage so much, but because of the other consequences that were conceivable based on this. But of course, this is also material modification. So quite an interesting perspective that without really focusing, you could create structures that are on the scale of the wavelengths. What you also see here is that it is not just a point. So but rather it's a structure of a centimeter of length, so much longer than the focus could have been if you would have used a lens or so. Right? And obviously what happens is that, well, that the laser beam is focused, and therefore the intensity in the focus is even higher than it was before, and therefore it still tries to self-focus. Well, at some point something happens. Here it is obvious, damage, right, which tends to defocus the laser beam, but soon afterwards it will be refocused again. The same can actually be done just in air. You may know this building here. That's the building we are in. And so this is the inner court. And people have used, well, I think it's almost 20 years ago, one of our powerful lasers and just shot it into the air. So this was published in Science later. Just shot it in the air, and if the laser is so intense that it self-focuses in air, then it can produce these, they are called filaments, then which are hundreds of meters long in this case. Right? And what happens there is that the laser is focused until the air is ionized, the molecules, the nitrogen and oxygen molecules are ionized, and then the free electrons, they lead to a defocusing of the beam, But as soon as the ionization is, as soon as the intensity is too low for ionization, this effect of defocusing stops, and the laser starts to refocus again, and this game can continue a couple of times and lead to a filament of this length. Yeah? So in other words, what happens there is that the laser beam is self-trapped. But actually, there are more trivial mechanisms that lead to defocusing of the laser. And the simplest and most obvious one is diffraction, right? And this is what we want to discuss next. Self-trapping and critical power. We want to ask ourselves, how much of laser power do I need in order to have this self-focusing angle so strong that it overcomes diffraction? Yeah? So this is the next point. And yeah, so when the power of the laser beam is so strong that it overcomes this diffraction, and then we would really observe self-focusing. Otherwise, if the power is too small, then diffraction would dominate, and accordingly, we wouldn't see the self-focusing effect. And the power at which this happens, yeah, so at which self-focusing becomes stronger than diffraction, this is called the critical power. And that's the headline here. So 8.4, self-trapping and critical power. Yeah, so you may wonder why I write critical power and not critical intensity. We'll see that. Okay, well, so in order to observe self-focusing, the self-focusing effect should be stronger than diffraction. Right? Okay, yeah? And well, the point at which they are equal, this will be the critical power. So what we do here is we counterbalance. Here we counterbalance both diffraction by self-focusing. So in other words, we demand that the diffraction angle is equal to the self-focusing angle. So that's equation 40. Okay, we use a familiar formula for the diffraction angle, namely diffraction at a circular aperture. So diffraction at a circular aperture. There we would have that the diffraction angle, if we define it the same way as the self-focusing angle, would be 0.61. Yeah, so if we speak about diffraction, then we usually use the full angle. And therefore, instead of 0.61, we have 1.22. So this is probably the number that is familiar to you, times the wavelengths divided by the refractive index, so that we have the effective wavelengths and not divided, lambda not divided by n naught. And and we set that diameter, that this is equal to 2 times the beam waist if we use a Gaussian beam, right? So this is kind of an approximate thing here, which certainly will give the right order of magnitude. Yep. And what we now do is that we plug in, well, the expression that we got for the self-focusing angle, so this expression here, equation 35, we plug into, well, equation 40 together with 41. So that would be the next point. So 35 and equation 40 and equation 41, I should write, in equation 40. Right? And then we find that 2 times and 2 times the intensity divided by n naught should be equal to 0.61 squared lambda naught squared divided by n naught squared d squared. And therefore, we find that the intensity is given by 0.61 squared lambda 0 squared divided by 2 times n naught times d squared. So that's equation 42. So we found an equation for the intensity at which self-focusing is as strong as diffraction. But if you look at this equation a little bit more carefully, then you find that we have actually here d2, so the diameter of the beam squared. So we have here an expression that is proportional to the cross-section of the beam. So it therefore would be appropriate to multiply it to the left-hand side of the equation. And then instead of the intensity, we have an equation for the power. Okay, so let's do that and then discuss it. So the power of a beam of diameter d is given by P equals the intensity times, the pi times d over 2 squared or so, right? And this means that the critical power is pi times 0.61 squared lambda 0 squared divided by 8 times n naught n2, and this is lambda 0 squared divided by 8 times n naught n2. Right, so all pi times 0.61 squared divided by 8, this is pretty exactly equal to 1. So this is the so-called critical power. Yeah, so when the power is larger than that, self-focusing will happen. And that looks strange, because what it says, that if you would try to reduce the intensity and therefore make the nonlinear refractive index, so N2 times the intensity, as small as you wish, this would change nothing. Well, so this should not influence whether the beam self-focuses or not. So you can increase the beam diameter, but nevertheless it would self-focus. It would eventually collapse and induce optical damage because the intensity is so high. Sounds strange, right? So expand the beam to 1 kilometer of diameter, and what I say is that it wouldn't help. The beam still would self-focus. And that's true, actually. But what we didn't say is how long it would take the beam to self-focus. We didn't say anything about the self-focusing distance. Yeah? So this property, that the fact whether the beam self-focuses or not is of course intriguing, but you find it actually not only here in this classical nonlinear optics, but you find it even in in the most extreme case of nonlinear optics, namely relativistic optics. And if you once attend a course by my colleague Maciej Kaluza, then he will certainly derive something at some point. Though there will certainly be a lecture on relativistic self-focusing. Yeah? And again, it will also only depend on the power rather than on the intensity, which really sounds strange, yeah? Because if the intensity is low and you can make it as low as you wish by making a kilometer broad beam, and you would say, well, the electrons, they don't oscillate relativistically. Well, but of course there is always a small relativistic effect, and it is sufficient. Yeah? But as I said, we didn't say how long it will take the beam to collapse. Yeah, so if it takes the beam a light year to collapse, you will never observe it here. And so the question on how long or what the self-focusing distance is of course as relevant as the question whether it self-focuses or not. But before we come to that, I would like to briefly mention another way to think about self-focusing. This is the following. We were talking here about trapping of light, right? So the self-focusing effect was stronger, or at least as strong as diffraction, and this gave us the opportunity to kind of produce a channel of light. Yeah, so where the light is always confined to a certain spatial region around the beam axis. This may sound familiar to you, at least if you know about optical fibers. In optical fibers, we do the same thing, right? We confine the light usually to a very small optical fiber. And how do we do it? Well, what we do is that we have a channel or a fiber of glass which in the center has a larger refractive index than at what we call the cladding. So there is a step in the index of refraction across the cross-section of the fiber. And this, if the angle of incidence on this cladding is small enough, then you have total internal reflection, and therefore the light is trapped. Right? And now we can do the same thing with our intense beam. And we could think and actually calculate and treat the entire thing as an optical fiber, basically. And you find this way to look at the problem in my script. Yeah, but because of reasons of time, we now want to go on and look at the self-focusing distance. This is then chapter, so we have 8.4. 8.5 would be the alternative way of seeing self-trapping. And so we come to 8.6, the self-focusing distance. So 8.6. The self-focusing distance. And so we go back to the figure that we had at the beginning of this chapter, namely this one here. And we write down another equation, namely an equation for, of course, the self-focusing distance. So from the figure, it follows that so that this W0, so the beam waist, is equal to the self-focusing distance times the self-focusing angle, or you can of course also write it in, so you can solve for the self-focusing distance. So we have omega naught divided by the self-focusing angle. For the self-focusing angle, we have already an expression, namely expression, so this equation 35. So 35, this equation says that this is the square root of 2 times n2 times the intensity divided by n naught. And if we plug that in, then we find the waist, the beam waist, times the square root of the refractive index divided by the nonlinear refractive index. And now we can use an expression for the intensity, namely that we have to divide the power through its cross-section. So omega 0 squared times pi. Then we find W0 times n naught times omega 0 squared times pi times 2 n2 times p. Right, and here you see that it's obviously dependent on the intensity rather than just to the power. But we write it as a function of power nevertheless, because we want to plug in the expression that we found for the power. Yeah? So, and this is what we want to do. We try to relate this power to the critical power. Yeah? So try to relate equation 51 to the critical power, for which we found an expression in chapter 8.4. All right, so the critical power, which is equal to lambda 0 squared divided by A times n naught times n2. And then we find for the self-focusing length, omega 0 times n naught times omega 0, W0, of course, times n naught times W0 squared times divided by 2 times n2. And then we write here, or we expand by the critical power. So we write P over P critical, and we undo this division by the critical power by multiplying with 1 over square root of the critical power. Right? And now if we do that, then we find 2 times omega 0 squared times n naught times square root of pi divided by lambda 0 times 1 over p over the critical power and the square root of that. Yeah? That's a useful formula, but if you think about it, so formula 52, if you think about it, then this formula obviously has a problem because, well, we said that if the power is smaller than the critical power, right, we shouldn't have, we don't have self-focusing. Yeah? So then diffraction is stronger than self-focusing. So this, but this is not reflected here, right? So if you make this thing small, you still get a finite value for that. Yeah, so what went wrong here? Well, quite obviously, I didn't use diffraction here, right? So I just wrote down this angle, the self-focusing angle, without correcting it with diffraction. Right? So let's make a remark here. Equation 52 fails if P is smaller. It also fails if P is equal to the critical power, because it delivers a finite self-focusing length instead of the self-focusing length going to infinity, right? So we neglected diffraction so far. So we would add diffraction now, and yeah, so we consider diffraction. And then we would write for the angle, so the combined angle, combined of self-focusing and diffraction, we would write it in this way. So the self-focusing angle squared minus the diffraction angle squared, and the square root of that. Yeah, and then we can do the entire procedure, the entire calculation with this corrected angle, and yeah, and after after some work, we find 2 times n naught times W0 squared divided by 0.61 times lambda 0, and then 1 minus square root of P divided by the critical power minus 1. And this is the important thing here, because then this self-focusing distance goes to infinity for the power going to the critical power, right? Okay, so that's enough for today. What I want to do next time, so we could continue discussing self-focusing for a while, but as I said, I think there are more interesting points, namely when the refractive index becomes time-dependent. When I use a short pulse, because then the time dependence is strong, when I use a short pulse, then as the pulse evolves, the refractive index changes, and if the refractive index changes, then it changes, then it affects, then it modulates the phase of this beam. So the phase is self-modulated, and now we have a time-dependent phase, which means that the derivative of the phase. And what is the derivative of the phase? Well, it's a frequency. So what it means is that we create new colors. And that's, of course, really the realm of nonlinear optics, namely to produce new colors. Yeah? And this is what we will start next time. But in order that you can really take advantage and appreciate what I will teach here, I would like to encourage you, well, I would like to urge you to look at what is the chapter 14 in this lecture, in my lecture notes. So if you look at the script, then you find what I covered today as chapter 12. And the next chapter is actually chapter 14. I realized this today, that this looks as if I would like to avoid chapter 13. This is actually not the case, yeah? So there's no superstition here. So this is, actually I don't remember what I wanted to cover in chapter 13, so maybe I have to renumber the chapters at some point. So please look at chapter 14, because this chapter discusses the propagation, the linear propagation of short pulses in dispersive media. This is a fairly long chapter, actually, but it does not belong to nonlinear optics, I would insist, because it's just linear propagation of a beam through media. And what we will do is, in subsequent chapters, is to just build on this chapter and expand it by a time-dependent nonlinear index of refraction, and we'll find all kind of beautiful effects. And those of you who started already, perhaps with doing some movie, might have seen some of these effects in my lab, and they are really colorful and beautiful. And yeah, so please look at chapter 14. Otherwise, you will have a problem following. So perhaps not already the next lecture, but certainly the lecture in 2 weeks. With this, I would like to thank you for your attention. Have a nice afternoon. See you next Monday.